We learn that a body which is located at a certain height above the ground, has also a certain amount of gravitational potential. In this case the ball has a maximum height of h sub I, therefore its potential energy is also at maximum value. If we steadily holding the ball, its velocity is zero, therefore its kinetic energy is also zero. But what happens if we release the ball? Of course, it will fall due to its weight. As it falls, it speeds up, so increasing the velocity to v sub f, and decreasing the height to zero. Since the ball gains velocity, therefore it also gains kinetic energy. So here we have a maximum value of kinetic energy. So what happens to the potential energy? Since the height has dropped to zero, its potential energy also becomes zero. We see that during falling, the potential energy of the ball is converted into kinetic energy. On the other hand, a rising body has initially a maximum value of velocity at its lowest position h sub I. At this position the kinetic energy is at maximum value, since the velocity is maximum, and the potential energy is zero when its height is also zero. Then as it rises, it decelerates due to its weight. So at maximum point of flight, it has a velocity of zero. At this point, since the velocity is zero, its kinetic energy is also zero. Its potential energy is at maximum value, since the ball has reached its maximum height. This illustrates that during rising, the kinetic energy of the ball is converted into potential energy. So what causes these conversion of energy? As you notice, on these two scenarios, the only force that acts on the ball is its own weight, or gravitational force. The weight of the ball converts its potential energy into kinetic energy as the ball falls. It is also the weight of the ball converts its kinetic energy into potential energy as the ball rises. So the weight causes the conversion from kinetic energy into potential energy and vice versa. And the force that offers two-way conversion of potential energies and kinetic energies is called conservative force. In addition to gravitational force, spring force and electric force are considered also as conservative forces. Here, the spring force converts elastic potential energy of the spring into kinetic energy of the ball. Non-conservative forces, on the other hand, are forces that tend to destroy the conservation of potential and kinetic energies. Frictional force is considered as of non-conservative forces. This is the reason why a pendulum, which is swinging due to its weight, slows down and eventually comes to rest. To illustrate this, here we have a pendulum, tied on a string, and it is hanging on a metal support. We mark this as the initial height or position of the pendulum. If we release the pendulum, it swings back and forth, converting its potential energy into kinetic energy, then to potential energy, trying to bring back the pendulum into its initial position. But do you think it will return to its initial height? What can you say? Of course, it will not return to its original height. On its way back, it swings with a height lower than the original. So it seems that the two-way conversion of potential energy and kinetic energy is destroyed. If this happens, it means that a non-conservative force acts on the system. So what is this non-conservative force? We see that there is a sliding contact happening between the string and the metal support, as the pendulum swings. The friction produces negative work between the string and metal support. This work is eventually converted into thermal energy or heat, which destroys the two-way conversion of potential and kinetic energies of the pendulum. So eventually, the pendulum stops. Without non-conservative forces, the pendulum will continuously swing virtually forever, but we know that's impossible. We see that a conservative force allows the two-way conversion of kinetic and potential energies of a body. If a non-conservative force acts on the body, let's say friction, it produces thermal energy resulted to a loss in the conversion of kinetic and potential energies. Nevertheless, the total energy of the system remains constant during the conversion of energy. In fact, at a speed relatively low compared to the speed of light, Energy is a conservative physical quantity and it obeys law of conservation of energy. It states that energy cannot be created nor destroyed, but only changes from one form to another. The following figures illustrates this conservative law. A diver on a springboard. The chemical energy in diver is converted to elastic potential energy in board, and then to kinetic energy on diver. Burning candle converts its chemical energy into radiant heat, that heats up the sardines. The heat energy from the combustion of fuel makes the gas expands, eventually transforming into mechanical energy. The chemical energy of the battery is converted to electrical energy, and to radiant heat and light energy. The chemical energy in person is converted to gravitational potential energy of the hammer, and to kinetic energy, do work in driving the nail. We already knew that when only conservative force, or weight, is acted on a body, then the two-way conversion of kinetic and potential energies can be observed. The sum of the kinetic and potential energies of a body is called total mechanical energy, denoted by letter E. Using this formula, we can determine the initial and final values of the total mechanical energies, either when the body is falling or rising. If we apply the law of conservation of energy, it is observed that the total mechanical energy of the body, considering only conservative forces, is constant. It means that the initial total mechanical energy of the body, E sub I, is equal to its final total mechanical energy, E sub F. Or that is the initial potential energy, plus the initial kinetic energy, is equal to the sum of the final potential and kinetic energies. And this equation is called the conservation of mechanical energy. In this illustration, we see that the total mechanical energy of 100 joules does not change. If the law of conservation of mechanical energy still holds true for a bouncing ball, it will return to original height and will bounce back repeatedly forever. But we know in reality it won't happen. Once a ball hits the ground, it immediately destroys the complete conversion of its kinetic energy into potential energy. Rather, some of the kinetic energy is converted into thermal energy, and sound due to its impact with the ground, and therefore the height of bounce will be a little shorter than its release height. As you can see, the initial total mechanical energy is 100 joules. As the ball hits the ground, the potential energy is converted partially into mechanical energy. It's because that there is other work done by non-conservative force. Here the value is 20 joules. This 20 joules will be converted into thermal energy, and may also produce sound. That is why the ball bounces at a lower height. But as you can see, even if there is some energy lost, due to this other work, still the total energy remains 100 joules. Take note, in this context, these other forms of energy, thermal, friction and sound, denoted by W sub other, is actually the work done by non-conservative forces acting in the body. With these, the energy conservation equation, if non-conservative forces are present, will become, the initial total mechanical energy is equal to the sum of the final total mechanical energy, plus the other work done by the non-conservative force. Now, in order to have clear understanding on conservation of energy, let us answer some problems. Problem number 10. You throw a 0.145 kg baseball straight up in the air, giving it an initial velocity of magnitude 10.0 meters per second. Letter A, use the conservation of energy to find how high it goes, ignoring air resistance. Letter B, what is the ball's total mechanical energy of the ball as it leaves the thrower's hand? Letter C, what is the total mechanical energy of the ball as it reaches the maximum height? Actually, this problem can be solved using the kinematic equations of free-falling bodies we have discussed in Unit 1. But this time we will use a different approach. We can solve this problem using the conservation of mechanical energy. Now, imagine this is the baseball of mass 0.145 kg, then according to problem, you throw it upward, so the initial velocity is 10 meters per second. So we gonna find, for letter A, the maximum height of the ball, h sub f. Take note, if we consider this our reference line or point, we set initial height h sub I, to 0. We knew it at maximum height, the velocity of the ball, v sub f, is 0. Letter B, we need to solve the initial total mechanical energy. And for letter C, the final total mechanical energy. So let's begin solving. For letter A, from conservation of mechanical energy, U sub I, plus K sub I, is equal to U sub F plus K sub F. Since the initial height h sub I, is 0 and the final velocity, v sub f is also 0. Therefore, the initial potential energy and the final kinetic energy are also zeros. So we can eliminate these from the equation. Hence, equation 1 is reduced to, initial kinetic energy is equal to the final potential energy. Then K sub I is, 1/2 of m, times v sub I squared. And U sub f is mg, times the final height, h sub f. From these equation, we solve for h sub f. We can cancel out the mass, m. So h sub f is, v sub I squared divided by 2g. Substituting the values. The initial velocity is 10 meters per second, then squared, divided by the quantity, 2 times 9.8 meters per second squared. So the maximum height reached by the ball is 5.10 meters. For letter B, the initial total mechanical energy is equal to U sub I, plus K sub I. Since the initial potential energy is 0, the total mechanical energy is also equal to the initial kinetic energy. And that is, 1/2 of m, times v sub I squared. Substituting the values, so the initial total mechanical energy is 7.25 joules. Lastly, for letter C, the final total mechanical energy is equal to the sum of U sub f, and K sub f. Since the final velocity, v sub f is 0, therefore K sub f is also 0. So the final total mechanical energy is also equal to the final potential energy. And that is mg, times final height, h sub f. Substituting the values. So the final total mechanical energy is also 7.25 joules. As expected, this value is equal to its initial value of energy, since we do not consider non-conservative forces. In problem number 10, we considered a rising body. In this problem, we will use conservation of energy to solve a falling body. Problem number 11. A ball of mass 0.3 kg is dropped from the top of a building whose height is 300 meters. Letter A, what is the velocity of the ball as it hits the ground? Letter B, what is the ball's total mechanical energy upon releasing it? Letter C, what is the ball's total mechanical energy as it strikes the ground? So imagine, this is the building, and this is the ball of mass 0.3 kg, located from the top of this building. The ball is dropped, therefore its initial velocity, v sub I is 0, and its initial height, h sub I is 300 meters. Upon reaching the ground, its height, h sub f becomes 0. So for letter A, we solve for the velocity, v sub f, as it reached the ground. Letter B, we need to solve the initial total mechanical energy. And for letter C, the final total mechanical energy. Now, let us solve this. For letter A, from conservation of mechanical energy, U sub I, plus K sub I, is equal to U sub f plus K sub f. Since the initial velocity, v sub I, is 0 and the final height, h sub f is also 0. Therefore, the initial kinetic energy and the final potential energy are also zeros. So we can eliminate these from the equation. Hence, equation 1 is reduced to, initial potential energy is equal to the final kinetic energy. Then U sub I is, mg, times the initial height, h sub I. And K sub f is, 1/2 of m, times v sub f squared. From these equation, we solve for v sub f. we can cancel out the mass, m. So v sub f is square root of 2g times h sub I. Substituting the values. So the velocity of the baseball as it reached the ground is negative 76.68 meters per second. We put here negative, since the ball's direction is downward, as it hits the ground. For letter B, the initial total mechanical energy is equal to U sub I, plus K sub I. Since the initial kinetic energy is zero, the total mechanical energy is also equal to the initial potential energy. And that is, mg, times initial height, h sub I. Substituting the values, so the initial total mechanical energy is 882 joules. Lastly, for letter C, the final total mechanical energy is equal to the sum of U sub f, and K sub f. Since the final height, h sub f is 0, therefore U sub f is also 0. So the final total mechanical energy is also equal to the final kinetic energy. And that is 1/2 of m, times v sub f squared. Substituting the values. So the final total mechanical energy is also 882 joules. As expected, this value is equal to its initial value of energy, since again, we do not consider. Okay, class, now it's your turn. Let us see if you really understand. Answer this exercise. Exercise number 6. Answer problem number 11. Except that, the ball is thrown vertically downward at a speed of 10 meters per second. Use conservation of energy to solve this problem. Conservation of energy can also be used to analyze the velocity of a roller coaster car at any point on the frictionless track. Problem number 12. The car of the roller coaster starts from rest at point 1. Neglecting air resistance and friction, find the car's magnitude of velocity at points 2, 3, 4, and 5. The only given information is the car's initial velocity at point 1, and that is 0, since it starts from rest. What we are going to do is to determine the velocity of the car at points 2, 3, 4 and 5. Since that the track is frictionless, and we neglect air resistance, so the two-way conservation of potential and kinetic energies is valid. And by conservation of mechanical energy, the total mechanical energy of the car at any point is constant. The car accelerates as it moves from point 1 to point 2. So to solve for the velocity at point 2, v sub 2, we will begin with E sub 1, equals E sub 2. So U sub 1 plus K sub 1, is equal to U sub 2 plus K sub 2. We will consider this line as reference line. This line is to be used to determine the height of the car. The height h sub 1, is 20 meters. Since v sub 1 is 0, so K sub 1 is also 0. The height h sub 2, is 0, since point 2 is already at the reference point. Hence, the potential energy at point 2 is also 0. So the equation is reduced to, U sub 1 equal K sub 2. U sub 1 is mg, time h sub 1. And K sub 2, is 1/2 of v sub 2 squared. We solve for v sub 2, so v sub 2 is equal to the square root of 2g, times h sub 1. Substituting the values. V sub 2 is 19.8 meters per second. Can you follow? Well, that's good. Now for the velocity at point 3, we can also say that, the total mechanical energy at point 1, is equal to the total mechanical energy at point 3. That is U sub 1, plus K sub 1, equals U sub 3, plus K sub 3. Again, K sub 1 is 0, so we can cancel this out from the equation. The height at point 3 is 12 meters, so do not cancel U sub 3, as well as K sub 3, since it still has velocity at this point. So the equation becomes, U sub 1, equals U sub 3, plus K sub 3. Transforming this equation, mg times h sub 1 equals mg times h sub 3 plus 1/2 of v sub 3 squared. Then, we solve for v sub 3, square root of 2g, times the quantity h sub 1, minus h sub 3. Substituting the values. So the velocity of the car at point 3 is 12.52 meters per second. We expect an answer lower than v sub 2, since that the car is decelerating, as it moves. Now for the velocity at point 4. We use point 1 and point 4, from which we are going to apply the conservation of energy. So u sub 1, plus k sub 1, equals u sub 4, plus k sub 4. Before we continue, we will assign this as our reference line, from which height is to be determined. So h sub 1 will now become 40 meters, and h sub 4 is 0, since it is already at the reference line. We can cancel out k sub 1, as well as u sub 4, since h sub 4 is 0. So the equation is further reduced to, u sub 1, equals k sub 4. We expand this to, mg, times h sub 1, equals 1/2 of v sub 4 squared. Then, we solve for v sub 4, square root of 2g, times h sub 1. Substituting the values. So the velocity of the car at point 4, is 28 meters per second. We expect an answer higher than v sub 3, since that the car is accelerating, as it moves from point 3 to point 4. Lastly, for v sub 5. This can be solved by observation. Since point 5 has the same level as point, therefore v sub 5 is also v sub 1, so the velocity of the car at point 5, is 0. It also means that, the car will stop at this point and it will not go further higher than this. Take note that, we analyze the problem on frictionless track. If friction is present, our answers will be different as compared to these values. In fact, if there is friction, the car will not reach point 5 by relying only on car's weight. In the end, it will stop at the lowest point at point 4, for as long as it reached point 3. Wow, congratulations for reaching this exercise. Answer this carefully, because this is quite challenging. Exercise number 7. A glider with mass 0.2 kg sits on a frictionless horizontal air track, connected to a spring with force constant 5 newtons per meter. You pull on the glider, stretching the spring 0.1 meter, and then release it with no initial velocity. The glider begins to move back toward its equilibrium position. A. What is its velocity when x equals 0.080 meter? B. What is the speed of the glider at equilibrium position?